Thank especially Stefan and Michael for the invitation. And I have to apologize to Michael because he has heard this talk already 2 weeks ago. But everybody else hasn't, so it's fine. So it's nice because the talk is very much related to in some sense, to what Julia has just talked about. So it's a very nice connection. I think that Julia has worked on similar topics a few years back. So it's also nice to meet her finally. Okay, so my expertise is non-autonomous differential equation. This is a session about climate in some sense. I wanted to put some context. These are some of the works that I've done in the past years with collaborators in Spain, so in Valladolid, at Imperial College, and in Munich, that are intended to characterize tipping point and critical transitions in a very specific context, which is the one in which you have a time-dependent variation of parameters. Okay, you have an underlying time-dependent system with a time-dependent variation of parameters, which typically is not slow, it's not adiabatic. Imagine increase of emissions for greenhouse gases with respect to the time scale of whatever, interglacial periods. I'm not an expert in this. Nonetheless, non-autonomous systems are very different from autonomous systems, and our take on this sort of problem is to try to characterize these tipping points, give them mathematical underpinning in the context of non-autonomous bifurcation theory. Because typically this time-dependent variation of parameters take place in range of parameters where there is no autonomous bifurcation. So you wouldn't see anything if you just do a usual bifurcation analysis or continuation. So just to do a few examples, what we have done, for example, for certain classes of scalar differential equations, we show that all these types of tipping points, rate-induced, phase-induced, phase-induced, or concave, deconcave, concave, convex equations are always non-autonomous sudden knot bifurcations, where you have a pair of hyperbolic solution, one attracting and one repelling, collide, and then they disappear. And this is, of course, much more complicated than the autonomous case because you don't have equilibria, you don't have direct access to these solutions, you cannot calculate stability easily because non-autonomous linear stability theory is much more complicated, and eigenvalues, they will just not work. And this is another example, which is a non-autonomously forced, non-periodically forced Fitz-Nagumo problem model where we studied the appearance of a non-autonomous version of the Hopf bifurcation. Yet another, there are many. In any case, when I arrived at Imperial, since I'm interested in discussing these critical transitions from the point of view of non-autonomous bifurcation theory, we try to understand what can we do if we put a bit of noise. Can we still talk of bifurcations? Now, with unbounded noise, there's quite a rich literature. Just a few references here. Sorry if any of your papers are not included. But what we are interested in is rather bounded noise. And why? Well, this is a recent work of mine with collaborators in Spain that represents a zero-dimensional energy balance model, for example, where you have a quasi-periodically forced model in red, temperature, atmospheric temperature, where the time dependency comes from solar irradiance and cloud variability, and then the gray sort of cloud that you see around, it's a perturbation through a continuous extension of a circle expansion map, so a chaotic process which represents a random, somewhat random bounded process around your deterministically quasi-periodically forced energy balance model. One representative would be, for example, this blue curve. Okay, so the good things about this type of bounded noise, in some sense, even though I haven't said anything about it, is that, okay, they are in some cases more realistic.
Always more realistic. There is no, energy cannot be infinite.
I'm glad you, as a climatologist, say that. The climatologist.
Unbounded noise is not physical. It's not physical.
Right, correct. Yeah. And one of the possible aspects is that they allow to analyze this phenomenon from a compounded point of view, where you can, at least in first instance, ignore the sort of probability distribution that comes with it and treat it from a topological point of view. In fact, you're dealing with localized objects in the phase space, which makes it possible for bifurcation theory, which you wouldn't have with unbounded noise, typically, not in the sense that we intended in deterministic sense. Okay. Now, just to make an example, clarify what this means, here I've taken a extended nonlinear van der Pol oscillator where beyond the unstable equilibrium and the stable periodic orbit, you have two more stable orbits, limit cycles. One is unstable in blue and the other one is in red. Just to show this to you. Oh, I want to say something else before I go there. Here I have, oh, how do I do this? Control L. Control L. Here you have certain parameters fixed, and then a special parameter mu that gives this representation of phase space. What I'm going to do now is changing mu with time and then add noise. Okay. So first of all, I'm going to simply change mu with time. What you'd see after a transient is that the only thing that will happen is that the internal stable periodic orbit becomes bigger and bigger without reaching any sort of bifurcation. It doesn't collide with the other one, it persists without any problem, but it's becoming a little bigger with time, okay? A bit as if it was a funnel. We are seeing sections of the attractors inside. Now what happens is when we add noise, is that at the beginning we'll see after a transient localized objects around these stable attractors, but then as soon as this stable periodic orbit in the middle starts to expand, some of the orbits that comes from the perturbation, I explain what they are and how they come through, they will just escape. So you will pass from having two localized objects to having basically one unique minimal invariant set.
But it escapes and it comes back?
Well, this is only, in fact, it's only 500 initial condition for 200 different perturbations. So it's very, I mean, you have infinitely many, very restricted sample. You don't really know what's going to happen, right? I mean, we can only make a guess because this is, but just a partial representation of what the phenomenon could be. Okay. All right. So, exactly this kind of picture. Pass from localized objects to a bigger minimal invariant set. Two minimal invariant sets to one bigger minimal invariant set. Okay, but there are also drawbacks with this kind of formulation. And in order to explain that, I want to go back for a moment to a simpler case, which is the one of autonomous and discrete time scenario. So we have a deterministic map, which is a dimorphism on an Euclidean space. This is small f. And then bounded noise, I just mean that I consider some perturbations that are restricted to the unit pole in RT with a certain amplitude of radius rho. So very specific, convex, symmetric, the unit pole. What happens, what is intuitively the dynamics, you take a point, you have your deterministic map F, you map it in another point, and now you extend it, you inflate it through a ball of radius rho. And this you're going to call it capital F, which is going to be your set valued map that goes from the point into the image, which is the closed ball of radius rho centered at the image of X through the map small f, which is your deterministic map. And then you can keep doing this. You apply small f again, and then you inflate it again to this additional map, and you keep going on. Okay. So this is more or less what we are dealing with from a discrete time autonomous point of view. Now, what is a invariant set for this kind of map? So it needs to be a non-empty subset such that the image through the set valued map capital F is exactly itself. So just intuitively imagine it could be something like this, where your deterministic map needs to map your set inside, so that when you inflate it again of this quantity rho, it goes back to the previous set. So you have to have some kind of dissipativity so that the noise compensates and create this sort of minimal invariant sets. Minimal, well, it needs to be a proper subset of M. It doesn't meet any proper subset, which was also invariant. Okay, now, what are the problems with this? This dynamical systems made like this requires a set valued formulation, which means that you have a dynamical system on the set of compact subset of the phase space, which is not the Banach space. So this is quite nasty. Typically, you don't have a lot of things that we use for dynamical systems in bifurcation theory. You don't have the implicit function theorem. Singularity analysis is very tricky. So there are many things that just don't work well. And also numerically, it's pretty hard because you're dealing with an infinite amount of possible perturbations for which you would have also infinitely many initial conditions. So there are techniques there. I'm not very familiar with this. There are selection techniques that allow to cope with this. But anyways, it's a very challenging setup. Good. So what was the idea that the group at Imperial had? So these are Coriolis, Lamb, Rasmussen, Tate, Imperial, Turayev. The idea was, okay, let's just talk about invariant sets, attractor typically inflated in this bounded noise scenario. And what we're going to do is just try to focus on the boundary. If we describe the evolution of the boundary, then the evolution of the rest will be inside. So we'll just deal with basically with the extreme case scenario. And it turns out that there's a very reasonable way of doing this from a discrete point of view, which is really geometric. You take a point, what you need is also to take into consideration the normal if you admit the boundary is smooth, a smooth manifold, the normal at that point to the tangent space to this manifold. And then once you apply your deterministic map f of x, what you need to do to come back to the boundary is using a new normal, which can be calculated through an adjoint problem, starting from your initial normal. So you don't only consider the boundary, but you consider an augmented phase space where you look at boundary plus point on the boundary plus normal at that point to the boundary. And what they showed is that, okay, you can consider now this map, which maps in fact every point and normal to image, which is f of x plus rho nu n, nu1 and 1, which is exactly the point on the boundary, and image of the normal, n2 and 1. And this object, which is the collection of these pairs, so they call it outward unit normal bundle, and they show that in fact that this is a minimal invariant, invariant with respect to the boundary map that I showed just before. So this is the result 0 that we would like to prove. They went way beyond this. They showed persistence. They did bifurcation theory because they looked also at the dual problem. But now, if we look back at our non-autonomous differential equation, this is the 0 result that we would like to prove to have formalism. Okay, so now we go back to non-autonomous, where we have now a deterministic part with a time dependency. This could be some forcing, or it could be your time-dependent variation of the parameter. And I'm not doing any E2 integration or anything alike. This is just a normal integration through time-dependent perturbation. So this is a continuous time non-autonomous problem, which has some issues. The biggest one is that, of course, you don't have you have a set valued in differential inclusion, and noise acts directly on the derivative, not on the trajectory, like in the discrete time case. So problems with that means that you have to define a flow. This is okay. You just define it collecting all the possible images of this of all the possible time-dependent perturbation of your initial equation. But more importantly, you cannot use the geometric approach because you don't have access to the trajectories anymore to describe the boundary. So the way you do it. Oh, and one more thing is that invariant sets now, they are not necessarily compact objects in the sense that they are sets that depend on time and change with time. And this setting, an invariant set will be a bundle, a family indexed with time, such that through your flow, the section at time t naught will be pushed in the section at time t. Okay, invariant means also that it doesn't, minimal doesn't contain any proper invariant subset. Well, in this setup, we can still define a unit normal bundle by collecting point pairs, point on the boundary and vector v, which is normal to the tangent space at the boundary. Easy peasy, but we'll have to look at all the sections in time and then collect all these sections into a new bundle, which is indexed with time. It's a complicacy, but this is completely fine. The most important result is that now we have invariance with respect to this set of differential equations. And so this unit normal bundle is invariant with respect to a set of differential system of differential equation, which is completely deterministic. It's a single valued, so it's not a set-valued dynamical system, and such that now you can apply everything that you know in dynamical systems theory, okay, which is a great outcome. Important, this is a boundary system, it's not a boundary map, so again, you don't have direct access to the solutions, but on the other hand, you also don't have any access to the solution of this differential equation in the first place, but you still can do qualitative analysis of the system. And the proof requires a non-trivial application of the Pontryagin maximum principle, because in fact, you can look at this as bounded noise, but also as bounded control, and this is something that comes, the proof comes from optimal control theory, in some sense.
Sorry.
Yes?
What happens when you project the solution of that system to the original one?
Yeah, I'll show this now at the end. I don't have enough time, but in order we study stability for these things, in particular, we looked at the linear systems. And one interesting thing that we showed, I'm going to skip through these slides because it's too much, that there's an attractor. You can do this unit normal bundle, everything is fine. And in fact, you can prove that this unit normal bundle is attracting in some sets, which means that you can also do numerics with it. You'll be converging towards this attractor in the higher dimensional space. So if you now look at the, for example, this linear case, what you see in blue are 500 trajectories corresponding to 500 different perturbations. It's a cloud. It doesn't really, it gives an intuitive representation of the volumes of the attractor there, but it doesn't say anything about the boundary. Whereas the red curves, they are the images numerically calculated of the projection on the phase space of the unit normal bundle through the boundary systems that I showed before. So I'm going to leave it at that. Thank you for listening to this. These are the people that paid for the job, so I'm going to say this, it's important. And these are some references. Okay, so these are the works on the boundary map, and these are some of my works on tipping points in the past years. Yeah. We look forward to publications.
So, yeah, very quick question.
Yes. Do you have the need of any particular hypothesis on the PBF of the noise term?
Right. So the interesting thing here is that at this stage, we're not really assuming anything on the nature of the noise. In particular, so we're just treating it as a topological problem, as an extreme case scenario in some sense. But in fact, if you saw, what I chose as possible perturbations was also essentially bounded functions that typically go even beyond the representation that we use an Ornstein-Uhlenbeck process for your noise, right? So it's something that's even discontinuous. But typically, you'll have maybe more information on distribution of noise, and this is something that necessarily will be, yeah, it needs to be integrated. Yeah, we'll have to do that, of course.
Thank you very much.
Yeah.
Yes, we have to move to the next talk, but thank you also for looking at this bounded noise, which is a difficult one.